ISTB presents, in association with Dhanmanjuri Community College, DM University, Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. What's spotted? Only on ISTB Nongin.
After the discovery of Mosebar effect by Mosebar in 1958, a lot of experiments which we postponed for a long time because we did not get a very high precision tuning clock. Now many scientists are able to do experiments which were postponed for a long time. One is about isomership. One is isomership. Number one. Number two, quadruple splitting. Number three, magnetic hyperfine splitting. Magnetic hyperfine splitting. And the last one, very important, is about the gravitational redshift. Gravitational redshift. Let us see what is isomership. When the Mosebar gamma rays, means gamma rays emitted without recoil free, it strikes to a similar nucleus. For example, let us take iron 57, and if we take natural iron, which contains about 2% of iron 57, that will absorb the gamma rays emitted by the Mosebar source iron. But there is certain difficulty because this iron, absorber iron and source iron, they are in different environment. Different environment will lead to the splitting or shifting of the nuclear levels. Therefore, such small shift of the nuclear level will lead to no absorption. One is the isomership. What is that isomership? Ground state, excited state. Now the surrounding of that nucleus which emits gamma rays, the electron distribution is different from the absorber. Your iron may be in stainless steel, your iron may be in chemical form, and the distribution of electron around the nucleus of the absorber and around the nucleus of the emitter, they are different. This leads to the isomership. This is isomership we have. This isomership is actually psi absorber mod square minus psi source. Means the surrounding wave function of the absorber and the source are different. This will lead to the isomership. Now let us see. Suppose if we take 14.4 kV gamma rays, and if we calculate, suppose if we take gamma rays, E gamma, which emitted by the iron 57, is E gamma is 14.4 keV, that is 14.4 into 10 to the power 3 electron volt. Okay, when you move this source, Mosebar source, which may be in any matrix, for example, change in the energy delta E gamma is equal to plus minus B by C E gamma. Now, if you put the value, suppose 1 millimeter, I move the Mosfet source 1 millimeter per second. So a very small amount. And you will find that the change energy, for example, V equal to 1 millimeter per second and C equal to 3 into 10 to the power 10 centimeter, 3 into 10 to the power millimeter into 11 millimeter per second, and E gamma is here. If you substitute this value, when you move the Mosfet source to and fro at a speed of about 1 millimeter per second, the change in the energy of the gamma ray is, if we put the values, it will be about 4.8 10 to the power minus 8 electron volt. So 4.8, if we put this value, we'll get about change in the energy will be delta E gamma equal to 4.8 into 10 to the power minus 8 electron volt. So we are talking about fantastically small energy change, which no one was able to do that earlier. It means Mosfet effect can be used in a variety of experiments. One is the isomershift, and many experiments have been done in the isomershift. For example, isomershift of, if you have iron in stainless steel, if you have iron 57 cobalt source, iron 57 in palladium, their surrounding environment are different. And if you take the spectrum, there will be shifting of the energy. Change of energy is 10 to the power minus 7 only, electron volt. Another is quadruple splitting, where the nucleus, second one, the nucleus, the charge is not nucleus of the iron. If the surrounding environment charge is not spherical symmetric, and it has got some quadruple moment about the surrounding charge, then that will interact with the nucleus. This will lead to the splitting of that iron. Iron, which has got excited state 3/2, and this ground state half. This will give the spectrum a doublet because of the what you call interaction of the quadruple moment with a nuclear quadruple moment and principal electric field gradient surrounding the nucleus, and this will give double splitting. This is what one will have. Beauty is that we know that this electric field does not remove completely the degeneracy which you have done in the perturbation theory. Magnetic field can remove degeneracy completely, whereas electric field like star effect does not remove the degeneracy completely. This is why the excited state of the iron, which is 3/2, spin 3/2, and ground state is half. The excited state is due to quadruple splitting. Excited state plus minus 3/2, and ground state is plus minus half. And the transition between these two will give you the quadruple splitting of the Mosfet effect. And this is such a small quantity. If you calculate how much energy is there, it is very easy. See how much millimeter we have. One can calculate. If it is about 5 millimeter, you multiply 5. Yes, the energy difference is so much between the excited state and the ground state. Now, why we come to nuclear decay scheme? Nuclear decay scheme of the iron. I have told you, cobalt 57, which is the excited state of iron 57. Naturally occurring iron is iron 56. 2% of naturally occurring iron contains iron 57. Now, cobalt 57, which is radioactive, captured the electron. It is 27, proton is there. It captures an electron, proton is converted to neutron, so it remains as 57. But however, number of proton has reduced to 26. So it becomes iron 57. The transition from 3/2 half, it gives to the 14.4 keV gamma rays. So this is used for a variety of experiments. Now we come to the experiment, how one does experiment. We have that source, and for that experiment, what one does is, you have this source which will be possible to move, with uniform velocity or with steep velocity using simple setup or using very complicated setup. For example, I have this source. This is source, Mossberg source. Source. Let us, because iron is equal to iron cobalt 57, which is possible to move with a small velocity, a few millimeters. Then you have the absorber here, and you have this absorber, and you have detector here. Detector. It's shielded with all the electronic circuit and others connected. This is absorber. What happened is that now this iron, cobalt 57, gives two gamma rays. One is 36 kV, another is 40. We have to separate these two. How one separate? Yes, one single channel analyzer, multi-channel analyzer using setup. Yes, this is done many years back, about 40-50 years back. This, using proportional counter. We see 6.5 kV gamma ray and 14.4. 14.4 is the Mossberg source gamma ray, which we are interested. Recoil free. 6.5 kV is the X-ray. When the electron is captured by cobalt 57, that vacancy, because proton becomes neutron, so electron in the case shell is vacant. So from L shell jump and X-ray is emitted to 6.5 kV. This is not gamma ray. Difference between gamma rays and X-rays is that gamma rays are emitted from the nucleus, whereas X-ray may be very high energy, low energy, are from the excited state of the electrons, filling the vacancy, electron knockout, filling that vacancy, it gives to the X-ray. So you separate this 14.4 kV and do the experiment. And this is what one can do. Stainless system, we have in stainless system, iron is there. Now, the iron, stainless steel, iron is there, cobalt 57, palladium matrix. The question is that the iron in the stainless steel, iron in the palladium, which is cobalt 57, which is excited state of iron. So what is the energy difference between these two? It is about, you see, 0.3 millimeter per second. And if I put it here, delta E gamma equal 4.10 to power minus electron volt is per millimeter. So the difference in energy due to environment change is fantastically small. It is about, multiplied by 3, about 12, 13 into 10 to power minus 8 electron volt. Fantastically small. Then you have iron in sodium nitroprusside. Then this iron nucleus in sodium nitroprusside, it has got some quadruple moment because of the surrounding, and this will give rise to two, Mossberg spectrum. So we will be able to know the energy splitting between these two. We come to here, see, means we will be able to know the energy difference between these two. The transition E pi and E sigma. The energy difference will be able to calculate from that. Because we know 1 millimeter corresponds to 4.8 10 to the power minus 8 electron volt. So at what velocity you are moving your source. Magnetic splitting, we call it hyperfine splitting. What we have? The nucleus has got the magnetic moment. It is 3 by 2. The spin is 3 by 2. Magnetic moment is there. And the transition This hyperfine splitting is the first time after the discovery of Mossberg effect, one is able to know the hyperfine splitting of the iron. Iron, which has got, see, now in the hyperfine splitting, as you have done in the perturbation theory, in the Zeeman effect, it is similar to Zeeman effect of the nucleus. The surrounding electron produces so much strong magnetic field interact with the nucleus magnetic moment, and that will lead to the splitting of the nucleus magnetic moment. So 3/2 half plus 3/2 half minus this, so it will lead to the transition of 6 lines. And we see that in the magnetic splitting, the degeneracy is completely removed. This is one of the very fine tuning experiment. This is what Mossberg experiment. So you have 6 lines, 1, 2, 3, 4, 5, 6 lines. Line taruk e. Line taruk asigi. So matai din asogi matai phausi about kainoni 12 millimeter per second gumni mana meter per second tawre millimeter per second. If you substitute the value in the how much the nucleus experiences the magnetic field due to the surrounding electron, it comes about 300 kilogauss, about 30 Tesla. Very fantastic, strong magnetic field experienced by the iron nucleus. So this leads to the magnetic hyperfine splitting. Now, the last one, which is one of the finest experiments that man has performed on this planet Earth. It is about the gravitational redshift. What is gravitational redshift? Yes, this is fantastic experiment because this experiment was postponed many years because you require very high frequency clock or which should be stable about 1 part in 10 to the power 15, 16. Means very high frequency you require. So what you have is, we have a gravitational redshift. What is gravitational redshift? Suppose I have this gamma ray or photon or light source. Suppose if I move from the earth to the above, this gravitational redshift says that the frequency or the energy of the photon or energy of the gamma ray will change. How much it will change, I shall not derive it. The change in the energy. For example, this is excited state, it emits gamma rays. This is ground state of iron. Now this becomes excited, gamma rays absorbed, recoil free emission, so this will give, and means when photon changes from one gravitational potential to the another, the photon will interact with the gravitational field, and this will lead to the gravitational redshift. One can calculate the gravitational redshift. It is very simple. So delta E gamma equal to mc. Yes. How much is delta E gamma change in the energy of the gamma ray or photon when it moves one gravitational field to the another is equal to what you have mass of the mgh, and mass of the photon is E gamma by c square gh. Therefore, the fractional change of the photon energy when it moves from one gravitational field to the another is equal to gh by c square. Fantastically small quantity. If we substitute the value of g, acceleration due to gravity on the surface of the earth, it is 9.8 or 10 if you say meter per second square. IC's height is 1 meter. Means when you take a photon or gamma rays from a source from surface of the earth above 1 meter, the gamma ray emitted energy will change gh by c square. And it is for 1 meter. The value comes out to the first scale is small. This comes into 1 meter. G you have ice equal to 1 meter, and Z you know 9.8 meter. Okay, c, you know, speed 3 into 10 to the power 8 meter per second whole square. If you substitute 1 meter, the value comes about, this comes about 1.1 into 10 to the power minus 16 electron volt. Minus 16, not electron volt. Yes. Means the change of frequency of the, or energy of the gamma ray, the change of the energy of the gamma ray is 1 part in 10 to the power 16. Thus, it means you can do one of the finest experiment on this planet. The gravitational redshift, we have this. The fractional shift in energy of the photon, according to this equation, is 1.1 parts in 10 to the power 16 per surface of the. When I take light, when I take source, that changes the frequency of the source. How much small? It is changing 1 part in 10 to the power 16. So at the 16th place of decimal, at the 16th place, only change is there. So now, so with the discovery of Mossberg effect, it has made available electromagnetic radiation whose energy can be measured with great precision. And the important parameter is fluorescent width, which is about, iron is about 3.1 into 10 to the power 13, zinc is 5. So people, they have done experiment. So with the discovery of Mossberg effect, it is now possible to observe the gravitational redshift and test equivalence principle. And this experiment was done by Pond and Replica in the Harvard Jefferson Laboratory, and they confirmed that, yes, gravitational redshift is there, as predicted by theory, and confirmed the gravitational redshift and equivalence principle of the Einstein.